This is a cube. I'm sure you're familiar with it. It has right angles on each side and its edge lengths are all the same. You can neatly stack them up, left, or right, or even all three at once. Cubes are interesting because they can infinitely fill a space, provided you have infinite identical cubes. A structure that infinitely fills space like this is called a honeycomb, and there are tons of honeycombs made of polyhedra like this. I don't really know why it's called a honeycomb because real-life honeycombs are actually just two-dimensional tessellations, but whatever. An interesting one is the octahedral tetrahedral honeycomb, which is made of octahedrons, like these, and tetrahedrons, like these, but why? These solids have nearly nothing to do with each other. Why can they fill space while most solids can't? Let's go back to the cubes. They fit so nicely because they're right angles. More specifically, the angle between two faces of a cube is 90 degrees. An angle between two planes is called a dihedral angle, and these dihedral angles come together so nicely that they can even fit around a single point. If you just erase the extra edges of the cube, you just get another smooth cube as shown. So what are the dihedral angles of octahedrons and tetrahedrons? This is actually quite a fun puzzle if you would like to try it out, and I'll give you a hint right now. The trick is to find the right cross-section of the solids, and we can start with this with a tetrahedron. If we want to take a cross-section which preserves the dihedral angle, we need to make sure that it is perpendicular to both faces. The best cross-section is the one that bisects the common edge of the two faces, which also happens to go through this opposite edge. And we'll assume that the tetrahedron has edge length 1, so this long side, which passes through an edge, is also 1. The other two edges are heights of equilateral triangles, which measure √3/2 each. We can now apply the lie of cosines to find the angle here, which, it turns out, is the arc cosine of 1/3. This angle is important, even if you don't know what it means, so just make sure to remember it. Now we can try octahedrons of side length 1. Again, this is also a very good puzzle, but it's pretty simple once you know how to do the tetrahedron. So if we want to get this angle, then we could just take this cross-section that bisects their common edge. And since this part is a square, this length must be 1. The other sides of this rhombus are heights of equilateral triangles, just like in the tetrahedron. Wait now. We've already seen this triangle, the tetrahedron, the triangle that has side lengths 1, √3/2, and √3/2. So this angle must be the same. But we aren't looking for that angle. We're looking for this one over here. It just so happens that the angles in a rhombus are supplementary. So the dihedral angles of an octahedron's faces and the tetrahedron faces will also be supplementary. This is a special relationship between octahedrons and tetrahedrons. They are perfectly flat when you put them together. This, combined with the fact that they both have equilateral triangles for faces, allows them to fit together so nicely in honeycombs. I'll show you this nice diagram of a honeycomb. As you can see, they fit together without leaving any gaps, and using them you can make any shape out of octahedrons and tetrahedrons as long as they fit this sort of cubic lattice pattern. This is technically called an alternating cubic honeycomb, although it has no cubes in it whatsoever, so I'm not really sure why. Now there are a couple other polyhedra honeycomb like this, but I want to showcase the rhombic dodecahedron right now. It's called this because its faces are all rhombi, and it has 12 of these faces. I'll only show a couple of them here because it would get really messy if I drew all the faces down the back of it, but just know that there are 12 of them total. The reason that it can fill the space is that from different angles, it will look like hexagons or squares. You can kind of imagine this in a 3D model. But again, it's a pretty bad drawing, so it's kind of hard to visualize here. So we know that this solid can honeycomb a space infinitely, and only by itself, too. That's pretty cool. Hold on, let's look at this rhombus face. What are the angles on it? Well, apparently, the angle is arc cosine of 1/3. Again. I just thought that this honeycomb pattern was pretty interesting to bring up because it showcases that this angle just happens to appear a lot in tessellations, or honeycombs, and three-dimensional geometry. It appears a lot. Anyway, that's all for today.